Welcome to the video for chapter 25. Today we're going to be talking about what to do if you find that the load impedance doesn't match the characteristic impedance of the line. We know that if they do match, then there'll be no reflections, and that's a very desirable thing for reasons we're going to talk about today. But how is it that you can correct the problem if you discover that there is a problem? So we're going to talk about 3 different methods for doing so. And in the process, we're also going to talk about the input impedance of a transmission line and how to calculate the impedance at any point, what happens if the transmission line is short-circuited or open-circuited. There are going to be lots of background discussions to be had. It's a relatively long lesson, but I'm going to try to go through it quickly so that the video stays at about an hour. Our historical perspective today is Alexander Graham Bell, because telephone lines were among the first transmission lines that were considered, and definitely impedance matching was important there to prevent the reflections that would cause echoes in the transmission lines. Telephone lines, telegraph lines, these were some of the very first applications. And so Alexander Graham Bell, who not only did he receive the first patent for a telephone, but he also founded the Bell Telephone Company, which later became AT&T. So let's talk a little bit about building on the knowledge that we gained last time. In chapter 24, we talked about transmission lines, and we derived an equation that allowed us to see what is the relationship between the voltage and the current at any point along the transmission line. The ratio of that voltage and current, we can call that impedance, and the impedance can be written in a variety of ways, but I've written it here in equation 25.1, including the reflection coefficients to show the relationship between the incident wave coming from the left and the reflected wave going back to the right. And then I have the characteristic impedance of the line, which shows the ratio between the voltage and the current. And then don't forget that this negative sign indicates that the reflected current is going to have an extra negative sign. We actually saw that in chapter 24, and I just want to remind you that we've discussed that. So obviously equation 25.1 can be simplified a little bit, and so you can see there equation 25.2, we've canceled out the v sub zeros, and the z sub c, which was in the denominator of the denominator, moved up into the numerator. As a matter of fact, we've moved it out entirely of that fraction. So now we have a good solid expression for the impedance at any point. We're furthermore going to substitute in what we know for gamma, which came from equation 24.25. So you can see that in 25.3, we've simply substituted that ratio in for gamma in both places where gamma occurred. Next up, we're going to multiply through by z sub l plus z sub c in the numerator and the denominator, and that's going to give us equation 25.4. Then we're going to group some similar terms together. We're going to put all of the z sub l terms together and all of the z sub c terms together. And then we get a combination of 2 complex exponentials, one of them positive and one of them negative. And those really remind us of the relationships for the cosine and the sine. One thing I wanted to draw your attention to here is that for the relationship with the sine, there's a negative here, and it has to be the positive minus the negative. But up here in our equations, we had the negative minus the positive. In both cases, we had negative minus positive, so that's going to give us a negative sine of kx. So when we replace the e to the jkz plus e to the minus jkz, that's going to become 2 cosine of theta. You know, we can take this 2 and move it over to here, just as we take this 2j and move it over to here. And you can see that we've got 2 cosine of kz in the numerator and 2 cosine of kz in the denominator. And then we have negative 2j sine of kz and negative 2j sine of kz. Again, because the order of those 2 terms needed to be flipped. And because it's a negative sign, when we flip them, it introduced another negative sign. So we could, again, we can divide through both the numerator and the denominator by 2 cosine of kz. So all of these 2's are going to go away. And the cosine divided by the cosine is just going to give us 1, and the sine divided by the cosine is going to give us a tangent, and we end up with this expression, which is the impedance at every point along a transmission line with a generalized load impedance. We don't really specify what the load impedance is here, but this is probably our most compact and useful form of this expression, and we're going to build on this in future examples. So we have a coaxial cable with characteristic impedance 100 ohms, and its length is 75 meters. It's attached to a signal generator set to 25 megahertz. The velocity of propagation is 2 times 10 to the 8th meters per second. Transmission line is terminated in a load impedance of 50 ohms. What is the impedance of the line at its input? Well, we know that the frequency is 25 megahertz. We know that the characteristic impedance is 100 ohms. We know that the load impedance is 50 ohms. And we know that the velocity is 2 times 10 to the 8th meters per second. So those are the known quantities. Let's now calculate the wavelength. So lambda is going to be the velocity divided by the frequency, which is 2 times 10 to the 8th divided by 25 times 10 to the 6th. That gives me 8 meters. So the wavelength of this signal is 8 meters. And let's calculate the wave number. So that's going to be 2 pi divided by lambda, which is 2 pi divided by 8, which is pi over 4. If you want the most precise answer, it's pi over 4, or you can write it out to 3 significant figures as 0.785. I'll tend to keep it as pi over 4 because it's important to get the answer as precise as we can. So the impedance at 75 meters, because that's going to be, actually it's at negative 75 meters. So let me try that again. So why won't you erase? Please erase, thank you. The impedance at negative 75 meters. Because remember that we have over here, we have the load, whatever the load is going to correspond to z equals 0. And if the line is 75 meters long, then whatever is at the other end of the load, this is going to be z equals negative 75. So the z is increasing in this direction, but we've defined z equals 0 to be at the load, so we have to say z equals negative 75 at the input. And so z at negative 75 meters is equal to 100, that's the characteristic impedance of the line, multiplied by 50, the load impedance, minus j times 100, the characteristic impedance, times the tangent of pi over 4 times negative 75. And then that's going to be divided by 100 minus j times 100 tangent of pi over 4 times negative 75. And that works out to be, because I know that this tangent right here turns out to be, negative 1, and this tangent right here turns out to be negative 1. This becomes 100 times 50 plus j 100 divided by 100 plus j 50, and that is equal to 80 plus j 60 ohms, or if you wanted to write it in polar form, it's 100 at an angle of 36.9 degrees ohms. And either of those answers would be correct. So the input impedance of this line is complex, which is interesting, but it's not unexpected because after all, the equation 25.8 has j that appears in it. It would be very unusual if the answer worked out to be a completely real number. And we're really accustomed to impedances that are complex. If you had a resistor and a capacitor, that would have a complex impedance, or a resistor and an inductor, that would have a complex impedance as well. So let's consider now, can we find a way to sort of pre-cook that answer that we just did so that it would be a little bit easier to use? Well, in this case, I guess I've redrawn the picture that I just sketched on the previous page, just reminding you that the load impedance is at z equals 0, and the input impedance would be measured at z equals negative L, where L is the length of the line. So Zn of a line that has a length of L is equal to the impedance of the impedance at the point z equals negative L. And when you plug in negative L into the previous equation, you get a negative sign inside the tangent, but the negative sign inside the tangent can be pulled in front of the tangent, and that turns those negative signs into positive signs. So while this equation is not very different than the generalized equation that we saw in equation 25.8, it is specialized for the input impedance of a line that has a length of L. And there isn't very much that's different in this calculation, but we will get the same answer. So Zn of a line that is 75 meters is equal to 100 times 50, and now it's just plus j times 100 times the tangent of pi over 4 times 75 divided by 100 plus j 50 tangent of pi over 4 times 75. So we get rid of a couple of negative signs in there, and that means that the calculation works out a little bit more smoothly, and that's equal to, again, 80 plus j 60 ohms, which is equal to 100 at an angle of 36.9 degrees ohms. If you are not pretty comfortable with using your calculator to do complex arithmetic, I would encourage you to become more comfortable. It's a skill that will benefit you not only in this class, but in other classes as well. Now, one thing that we can prove, and I'm not gonna dig into the details here, but we can prove that the impedance along the line repeats itself every half wavelength. So whatever it is that impedance is doing, it's going to have a cycle, and that cycle is going to have a wavelength. It's going to have a repetition every half wavelength. And so what we're proving here in these equations, and again I'm going to sort of skim past this a little bit. What we're doing is we're proving that Zn of L plus lambda over 2 is equal to Zn of L. So if we look at what does it look like at L, it's going to be exactly the same thing at lambda over 2. And it's going to be the exact thing at the next lambda over 2 and at the next lambda over 2 and so forth. So it's just good to know that the impedance will repeat itself every half wavelength. Whatever it's doing, it's going to repeat itself. And we'll see two examples of that coming up very, very shortly here. Now, it turns out that the input impedance of a line that is exactly 1/4 wavelength long has a very special characteristic, and so we're going to talk about that. We're going to start with equation 25.10, which is our equation for the input impedance of the line. We're going to plug in L equals lambda over 4. So we have lambda over 4 here, and we have lambda over 4 here. We're going to replace K equals 2 pi over lambda, and then the lambdas, let me erase those, the lambdas are going to cancel. And then the 2 pi over 4 becomes pi over 2, but then the pi over 2, the tangent of pi over 2 is infinity. Well, if we had, and again, this is not, a mathematician would lose their mind if they saw me writing it this way. Again, it is a limit, so I want you to know that I know it's a limit. But if we took that limit, then the z sub L and the z sub C would drop out. And because these infinities came from exactly the same quantity, tangent of pi over 2, they'll cancel each other out. The j's are going to cancel each other out. And what we end up with is z sub C times z sub C over z sub L, which is to say z sub C squared over z sub L. And it may not seem particularly special or particularly helpful, but it will be very special and very helpful to us as we're moving forward. So while the input impedance of a line in general can be a pretty complicated equation, which involves often complex numbers, this one is completely real, and furthermore, it's very easy to calculate. So it's something that will be beneficial to us moving forward. Let's also consider two special cases. What happens if the transmission line is matched? So if the impedance of the load is equal to the impedance of the line, then we can plug in z sub C for z sub L, and the numerator and denominator of this fraction are equal to each other. So they cancel each other out, and we're just left with the impedance of the line is equal to z sub C. So take a minute and just consider what that means. If I have a line and it's terminated in a load, and the load is z sub C, and the line is z sub C, then it looks as though that load isn't even there. It looks as though the line is infinitely long because you never get any reflections. So if you're just looking into the line right here, you see that Zn is equal to Zc. So that's good to know. And ultimately, remember, our goal here, our dream is that z sub L is equal to z sub C. That's what we're striving for because we don't want reflections. So if you have an impedance matched transmission line, the input impedance is equal to the characteristic impedance of the line. Now let's consider what happens if the line is short-circuited. So in other words, you've got a line where whatever the transmission line is, at the end we're just going to short-circuit it. So there we know that z sub L is equal to 0. And what does the input impedance look like if we're going to look down here? So it has a characteristic impedance of the line, and there's a length L, So what is that input impedance? Is it just 0? Well, if this weren't a transmission line, it would just be 0. It would just be a short circuit. But now we've got the transmission line to deal with, so it's not just 0. But if we plug in 0 for Z sub L here and 0 for Z sub L here, well, those terms go away. The Z sub C's are going to cancel, and we're left with just J Z sub C times the tangent of KL. So that's going to be a very useful equation for us as we're working with quite often, as a matter of fact, we're going to be working with transmission lines that are either short-circuited or open-circuited. So let's calculate the input impedance of the transmission line from 25.1 if it's short-circuited rather than terminated with a 50 ohm impedance. So there, Z sub N of L is going to be equal to J Z sub C times the tangent of K times L, which is equal to J times 100 times the tangent of pi over 4, that's the K, times 75 meters, and that works out to be negative J 100 ohms, which you could write as 100 at an angle of negative 90 degrees ohms. So we're going to find that the input impedance of a line that is short-circuited is always going to be perfectly imaginary. It'll either be a positive J or negative J with an amplitude on it. But in this case, in this particular case, it turned out to be negative J. And just reminding you of the complex axes here. So we're pointing in the negative J direction. And since we're in the negative J direction, that's where the negative 90 degrees comes from. So it'll always either be positive or negative J. And here's a plot that shows what does that impedance do. And notice that here I've used X sub M because this is going to be an imaginary impedance. So this is imaginary. So that's X sub M. And what does it look like for various lengths of the line? So notice that this axis is L divided by lambda. So if the line is infinitely short, well, that must mean that it's not even a transmission line. It's just the short circuit. And good, that's what we would expect. That for a short-circuited line that's not really a transmission line, we would expect that it would just be short-circuited. But notice now that any value of imaginary impedance can be obtained by simply selecting the length of the line. So if you said to me, hey, I want this line to have an impedance that is J10 ohms, well, I would say, you know what, that line right there with that length, or this line right here with this length, or this line right here with this length, actually, yeah, these are negative lengths, so that won't work. But these two would work. You could have any impedance that you want. You can get a line that will match that simply by choosing the correct length. And similarly, if I said I want negative 15 J ohms, well, then I could choose these lengths right here. So it's just a matter of using equation 25.25, so this equation right up here. If you tell me what impedance you want, I can then calculate the length of the line that will give you that impedance. We're gonna call that back at the end of today's chapter. So I just want to really hit it home real hard that we do have this plot that shows that any impedance that we would desire can be obtained simply by selecting the length of a short-circuited line. Next up, let's consider what is the input impedance of an open-circuited line. So if you have an open-circuited line, that just means that the line comes down here and there is simply nothing attached to it. And so if there's nothing attached to it, then the load impedance is infinitely large. And when that happens, we can quote-unquote plug infinity into the 2 points where Z sub L appears. If we do that, then the other terms are going to become insignificant. And since each of these originally came from a Z sub L, then those can be canceled out. The J in the denominator becomes a negative J in the numerator, and the tangent in the denominator becomes a cotangent in the numerator. So you could either use this equation right here, which is fine if you're like, I'm not all about the cotangent, but I am fine with having a tangent in the denominator, or if you want a nice compact version of the expression that looks a lot like the one for the short circuit, then you could use that one. So this is the impedance, the input impedance of an open circuited transmission line. And we can plot this one. I'll come back to that example. We can plot it again, and notice that a couple of things happen. That if the line is 0 in length, then we do in fact find that it's a short circuit, as it must be. And again, if you said, "Hey, I'd really like to have a line that has an impedance of 5 ohms," well, it's actually there's 2 points here. They're almost on top of each other, but there's 2 points that would give you that impedance, and then every half wavelength, it's going to repeat. Remember, we said that all lines have an input impedance that repeats every half wavelength. Well, this is demonstrating that because at 0, at 0.5, at 1, we can see that the pattern is repeating itself every half wavelength. So both for the short-circuited and for the open-circuited, we're seeing good examples of this half wavelength repetition. Let's go back up and hit this example 25.4. The input impedance of the transmission line described in example 25.1 if it is open-circuited. So we're really getting a lot of use out of that transmission line. This is going to be, because I don't have a cotangent button on my calculator, I'll use negative j z sub c divided by the tangent of k times L, which is negative j times 100 divided by the tangent of pi over 4 times 75. And when I do that calculation, I get plus j 100 ohms, which is 100 at an angle of 90 degrees ohms. Where again, because it's plus j, I know that it's pointing in the upward direction, and that's why this is positive 90 degrees. So we've seen a lot. We've seen how to calculate the input impedance of a transmission line. We've seen how to deal with it if it has a short circuit, how to deal with it if it has an open circuit. We've proven that the impedance is going to repeat itself every half wavelength. That'll come back up in chapter 26. And then we also saw how to deal with the special case when the line is just exactly a quarter of a wavelength long. So all of that was kind of leading up to the impedance matching. Now, it turns out that there are several reasons why we'd really like the line to be impedance matched. I mean, ultimately, let's look at these 4 cases. Ultimately, what we want is we're sending a signal to the load for a reason. Very often, this load is going to be an antenna. And if we're sending a signal to an antenna, our hope would be that the entire signal would be absorbed by the antenna and radiated away into free space. You know, if only half of the signal is being absorbed by the load, then we're wasting half of the energy. And so we definitely don't want to have half of our energy be wasted. When the reflected wave interacts with the incident wave, the maximum voltage can be higher than the amplitude of the incoming wave. Remember that we talked about that VSWR, the voltage standing wave ratio, and we saw that the peak can actually be far above what the amplitude of the incident wave is. It can be a factor of 2 higher, and so typically a coaxial cable or a transmission line is going to cost more in order to be able to handle higher voltages. So we're going to end up having to pay extra to get a better transmission line to hold a higher voltage if we have these reflections dealing with it. So if we can prevent those reflections, then we can have lower voltages and therefore less expensive cables. The reflected signals will eventually return back to the transmitter. You know, if I've got a transmitter here, I've got a whole long line, and I'm sending a signal down, but part of that signal is getting reflected back. Well, what's going to happen when that signal hits the original source? It may or may not be designed to handle incoming signals. I mean, it can generate signals, but it might be damaged if a reflected wave comes back to it. And so we need to be careful not to damage our sources, and that's one of the reasons why we want to prevent reflections. And then finally, and perhaps most importantly, it's very likely that the reflected wave will also reflect off the source end of the load, the left end of the wire, and then it'll create an echo of the original signal sometime later. So if we go back up here to this sketch that I drew, you know, I have a signal coming down and it reflects back. When it hits this transmitter, let's imagine it doesn't destroy the transmitter, but some of it's going to reflect back again. But it's going to reflect back 2 delta t later. So the first wave is going to hit the load, and it's probably going to transmit it out as an antenna, but then 2 delta t later, the second one's going to hit it, and that's also going to send it out. So maybe that just means you'd hear an echo on the line, but maybe it means that you're transmitting digital data, and it gets and the receiver is going to get confused by the second copy of that packet. worst case scenario, it says, hey, debit $1,000 from my checking account, and it receives 2 copies of that signal and debits it twice. Now, in reality, that wouldn't happen, but you understand that there could be complexities that would be created by the reflected signal. And maybe it's going to reflect more than once. Maybe you'd have an echo, 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 and so you'd have several copies of the signal that you would have to deal with, and we don't want that. If we can just match the line to the load, then we'll get no reflections and we won't have to deal with any of these things. So ultimately, we have 3 ways to match the line to the load. And each one of these ways, the job is to make it look like the load impedance matches the line impedance, even when it doesn't. So we're going to have something that we're going to do to make it look as though the load matches the line, even though it doesn't. Because we're going to assume that we can't change the line impedance. Maybe this transmission line is too long or too expensive or too inaccessible to change. And we're also going to assume that we can't change the load. Maybe this is a 50-foot antenna, and we can't change that antenna, or it's some sort of proprietary antenna, and we don't have access to change the impedance of that load. So if we can't change the line and we can't change the load, we're going to make it look like the load matches the line. We have 3 methods for doing this. We have the quarter wave transformer, we have the parallel load, and we have the single stub tuner. And the first 2 of those each have some shortcomings, and ultimately our best solution is going to be the single stub tuner, but there are strengths of the other 2 as well, so let's look at those. So the quarter wave transformer simply says we're gonna break between the end of the line and where the load occurs. We're going to break and we're going to insert a little chunk of transmission line that is exactly a quarter of a wavelength long. And we know what Z sub L is, and we know what Z sub C is, and ultimately our goal is that whatever Z sub 2 is, Z sub 2 needs to match Z sub C. Z sub 2 is the combination of that little quarter wavelength stub, I'm sorry, I should call it a quarter wavelength transformer, terminated in the load impedance. So that combination, the combination of these 2 right here, needs to match the characteristic impedance of the line. Well, we actually know how to deal with a quarter wavelength piece of transmission line. We have equation 25.21. It's Z sub C squared divided by Z sub L. So we know that Z sub 2, so this is Z sub 2, Z sub 2 needs to be equal to that quantity, and it must be that matches that matches what is the characteristic impedance of the line. So we're going to say Z sub 2 is equal to Z sub C of the quarter wavelength transformer squared divided by Z sub L, and we know that must match the characteristic impedance of the line. So we know Z sub C and we know Z sub L. What we don't know is Z sub C of the quarter wavelength transformer. So if we solve equation 25.30 for Z sub C of the quarter wavelength transformer, we get that it is the square root of Z sub C times Z sub L. That's sometimes referred to as the geometric mean of those 2 numbers. So let's imagine that we had the example of 25.1. So we have Z sub C is equal to 100 ohms, and Z sub L is equal to 50 ohms. Let me just double check that I didn't get those 2 backwards. Nope, that's correct. And so then it just means that we would need Z sub C, we would need to locate a piece of transmission line that has a characteristic impedance, which is Z sub C times Z sub L square root, which is the square root of 100 times 50, which is equal to 70.7 ohms. And the length of that is going to need to be a quarter of a wavelength. The wavelength was 8 meters. We calculated that back in example 25.1. Divided by 4 is 2 meters. So if we separate the load from the line and we insert a 2-meter piece of 70.7 ohm transmission line, then it will appear as though the line and the load are matched to each other. Let me just go back up again to the figure and just remind you that basically what we're doing, I'm going to erase the marks that I made before. What we're doing is we're taking the combination of these 2, using this equation right here. We're going to take the combination of those 2, we're going to set them equal to the characteristic impedance of the line. So this actually seems like a pretty good solution, right? This seems like it's not going to be too hard. The calculation was actually quite easy, but here's the problem. You go to the transmission line store and you can get several choices. You can get, probably 50 ohms, 100 ohms, 200 ohms, but you probably can't get 70.7 ohms. It's going to require a very specific characteristic impedance, which you probably don't have. And if you wanted to build that from scratch, it would be extremely expensive to build that 2-meter piece of line. So requiring a very specific and very precise characteristic impedance for the transformer kind of makes it so that this method is not as useful. If it just happens that the math works out and you happen to have a piece of transmission line that gives you what you need, then that's great. This is the easiest of all the methods, but usually you won't, and usually you won't be able to buy it off the rack. Parallel load matching. So here we're going to simply take the load impedance. Remember that we have this load impedance here, and it is a mismatch to the characteristic impedance of the line. We're just going to put another impedance in parallel with that one and take the combination of those two and match that to Z sub C. So let's do the math on this one. We know that that the parallel combination of Z sub Q, which is the extra impedance that we're adding, with Z sub L has to be equal to Z sub C. So we can write these as admittances, and then if we do that, then 1 over Z sub C equals 1 over Z sub Q plus 1 over Z sub L. We can solve that equation for Z sub Q, and we get an equation that says, hey, you want to put an impedance in parallel with Z sub L? This is the impedance that you need. So it turns out that if you place an impedance, and you probably already know this, if you place an impedance Z sub Q in parallel with Z sub L, you can only ever decrease Z sub L. You can never increase it. So it's not possible to match Z sub L to a line that has a higher impedance. You can only lower the impedance of the load. So that's important, that if you have to match it to a smaller line impedance. So let's calculate the parallel load that would be needed to match a 100 ohm load to a 75 ohm line. Again, we're doing a lot of the pre-math here, or a lot of the math is sort of being pre-done for us, which means that the actual calculation is actually not that hard. There will very likely be a question about impedance matching on the next exam, and you will likely be very happy with that question because it's not hard, as long as you understand what these equations mean. So as you can see here, that if we have a line that is 75 ohms, and we have a load which is 100 ohms, then the easiest way to match those is to add another load directly in parallel with this that is 300 ohms. And if we do that, then we'll end up with the combination of these two being 75 ohms. And since what the line sees is that combination, the line thinks that everything is happy and everything is matched. You can also do this again in terms of admittances. So I just wanted to point this out because when we work with Smith charts in chapter 26, we're going to be working largely with admittances. So that strategy again will only work if the load impedance is higher than the line impedance. If it's the other way, then we also have a solution, and that is we're going to move the extra impedance, we're going to move it a quarter of a wavelength away from the load. So before, we put it right at the load. We literally attached it to the same point as the load. Now we're going to move it a quarter of a wavelength back. And so again, the combination of these two is going to be equal to Z sub C. So how can we calculate the combination of those two? Well, we know that Z sub n of lambda over 4 is going to be the combination of a quarter wavelength of line terminated with the load impedance Z sub L. And remember that we have this special case. That is going to be Z sub C squared divided by Z sub L. And this is just the same old Z sub C that we had in the previous line, because it is the previous line. All we did was work our way back a quarter of a wavelength, cut the line, and maybe we didn't even have to cut the line, but we're going to put a load in parallel with the original load a quarter of a wavelength away. So we know that Z sub n of lambda over 4 is equal to Z sub C squared over Z sub L. We're going to put that in parallel with Z sub Q. So we're going to take that quantity and we're going to put it in parallel with Z sub Q, and we're going to set that equal to 1 over Z sub C. So again, you could think of this either in terms of impedances or in terms of admittances. If you then solve that equation for z sub q, because that's what we're ultimately looking for, you get equation 25.37. I'm then going to take this quantity and plug it into that quantity right there, and that gives me this quantity right here. Develop a common denominator, and then flip the denominator up into the numerator, and we end up with this expression, which tells us that if you want to match a load that is lower than the impedance of the line, then move the extra impedance a quarter of a wavelength back and give it this amount of impedance. Again, alternatively, you could perform the calculation using admittances, but impedances in this case seem to be easier. So how would we use this technology to match the example problem from problem 25.1? Well, the amount of impedance, z sub q, is going to be equal to z sub c squared divided by z sub c minus z sub l. That's going to be equal to 100 squared divided by 100 minus 50, and that's equal to 200 ohms. And where do we put it? We put it at lambda over 4, which is equal to 8 meters over 4, which is 2 meters away. So the original system looked like this, and we had a load, and it was 50 ohms, and the line impedance was 100 ohms. We're going to work our way back 2 meters, and we're going to put another load 2 meters away, and that's going to be 200 ohms. And it's not as obvious to us, it's not as intuitive to us that that combination is going to be equal to 100 ohms, but it is. This combination is equal to 100 ohms. We just did the math to prove it, and so now we see that that combination is going to match the characteristic impedance of the line. But there is a problem with this method too, and that is that these extra impedances that we're adding are still going to be absorbing energy. Although they're not going to have reflections, because they're essentially going to be resistors, they're still going to be absorbing energy, and so we need to. This overcomes a few of our concerns with having reflections, but it doesn't overcome all of them. And one of the concerns is that maybe now we're only delivering 80% of our signal to the load, and the other 20% is being wasted on this extra impedance. Furthermore, if this is a big antenna that's receiving a lot of voltage, a big signal coming in, this might need to be a really physically large piece of impedance that can dissipate that incoming voltage as heat. So, again, this is a solution, but it's not necessarily the best possible solution. Single stub tuner is probably the best possible solution. So when we talk about single stubs, I want you to always picture, and there's a lot of words here, I would say read these words, but what we're going to do is we're going to add a stub to the line. We're going to move back a certain distance, d1, away from the load, and we're going to add a stub that has a length of d2. Now this stub is actually composed of the same material as the original line. You know, if you have that line, you probably have extra pieces of the material. So if you had an extra meter or two of that line laying around, you can probably correct whatever problem you have in the mismatch simply by going back a distance of d1 and inserting this stub that it has a length of d2. Remember that this stub is essentially acting as an impedance. And in particular, we could choose this to be a short-circuited stub or an open-circuited stub. We're going to tend to choose the short-circuited stub because the open-circuited stub tends to act like an antenna of its own. So it would radiate the energy away, and that's not what we're looking for. We're just looking for it to correct the mismatch between the load and the characteristic impedance of the line. So we're usually going to use a short-circuited stub, but we need to choose this distance d2. By choosing that distance d2, we're really choosing what is the extra impedance that we're putting in place. And we aren't any longer going to just move back a quarter of a wavelength. We need to move back a certain distance so that whatever this distance d1 is, that zq combined with whatever the input impedance of that combination is going to match the characteristic impedance of the line. If all of those words were a little bit confusing, just remember a couple of things. We're going to move back d1. We're going to put in parallel a stub that's going to be short-circuited, and it's going to have a length of d2. Now we know that in essence we need to have the parallel combination of Zn1 with Zn2 has to be equal to Z sub c. because that's going to be the impedance that's seen by the line. So we could say 1 over Zn1 plus 1 over Zn2 equals 1 over Z sub c. But I think that it's easier to work with admittances here. The math is going to get a little bit hot and heavy for the next couple of minutes, so let's leave it as impedances. as admittances. And we know that if we're looking at a short-circuited stub, we already know that the impedance is J Z sub c tangent of KD over 2. That's from equation 25.25. To get the admittance, you're just going to invert that. And then we also know that if whatever y sub n1 is, y sub n1, if we look at equation 25.10, remember that the numerator and denominator are flipped for an admittance, but this is exactly what the input impedance of a line that has a length of d1, a characteristic impedance of z sub c, and a load impedance of z sub l would look like. We're now going to combine these two together in parallel and set them equal to the admittance of the line itself. So we have the admittance. This is yn1. So this is yn1. This is yn2, and this is yc. So yn1 plus yn2 equals yc. And now it's just an exercise in algebra. We're going to multiply both sides of that equation by z sub c to get rid of some z sub c's that were in the denominator. So we'll simplify things a little bit. The right-hand side in particular just becomes 1. Now we're going to multiply through by this denominator multiplied by this denominator. All three terms are going to get that. And of course this first term, when we multiply through, it's just going to get the j tangent of KD2 is the only thing that's going to multiply this term. And this one is going to only get z sub l plus j z sub c tangent of KD1. So that's this quantity right here. But then the right-hand side is going to get both of them multiplied together. So we're multiplying through by the product of the two denominators on the left-hand side. And we get an expression that spans a couple of lines because there's a lot going on here, but there's no longer a denominator. We're going to multiply out both sides of we're going to multiply out all the terms in both sides of the equation. And we end up with the expression shown in 25.48. Now the interesting thing about that equation is that it is a complex equation. There are imaginary terms. There's an imaginary term, there's an imaginary term, there's an imaginary term, and then there are real terms. That's a real term, that's a real term, and that's a real term. In order for equation 25.48 to be true, and it is, then the imaginary terms must be equal to each other and the real terms must be equal to each other. So a complex equation really contains two equations. It has the real parts and it has the imaginary parts. So let's consider the imaginary parts first. I'm going to take this term right here and this term right here and this term right here. And I'm going to set them equal to each other. I can divide the j's, so the j's are going to go away. And then I'm going to move the d1 term over here and the d2 term over here. And I'm going to divide by z sub c to isolate just the tangent term. This equation is very helpful to us. And we're going to sort of take that equation, we're going to put it on a shelf for the moment. But we're going to come back to it. Now let's do the real parts. So I'm going to come up here and I'm going to take the real parts, which is this one, and this one, and this one, and I'm going to set them equal to each other. I get equation 25.52. Rearranging, moving things over to the right-hand side, I get equation 25.53. And then I can substitute, here notice that I have a tangent of KD1 right here. I'm going to take this equation and substitute it in for the tangent of KD1. And that's really where this term is coming from. I can simplify because now I have a pair of tangents of the same thing, so that becomes the tangent squared. And then this z sub l minus z sub c and this z sub l minus z sub c becomes z sub l minus z sub c, the quantity squared. Don't forget this z sub c here comes down to there. So we have an expression here which is z sub l and z sub c, which are known, and k, which is known, and d, which is d2, which is not known. So we're going to solve that equation for d2. And when we do that, we have now figured out 1/2 of the problem. So d2, I just want to remind you that if I scroll back up again, d2 in this picture, d2 is the length of the stub. So what we've figured out now is how long does that stub definitely need to be for the single stub tuner. And then for D1, we can then go one step further. We're going to combine, let's see, I'm going to go back up to equation 25.51, which is this equation right here, the one that I said we were a pretty big fan of. I now know what D2 is. So I'm going to plug what I know for D2 into equation 25.51, and then I'm going to solve it for D1. And that's where I get this equation right here. So notice that I know K, I know Z sub L, I know Z sub C, I know Z sub C, I know K, I know D2 because I just found D2 up here. Now, yeah, I could take this quantity right here and I could substitute it in for D2, and that would make equation 25.57 a nightmare. So that's why I'm not doing that, but I just want you to know that you must solve for D2 first before you can solve for D1. But if you do that, you're going to end up with these expressions, which are actually not too hard to work with. It's actually very nice. One thing I'll make a note of here is that this inverse tangent is relying on the fact that these are in radians. So when you are working with this inverse tangent with your calculator, you must make sure that you're in radians mode. If you're not, you're going to get the inverse tangent wrong. And then just as one last reminder, the most common mistake that people make on a problem like this is to forget which one is D1 and which one is D2. So D1 is the distance from the load where the stub must be placed, and D2 is the required length of the stub. So you calculate the length first, and then you calculate the location. That brings us to our last example for today. Design a single stub tuner to minimize reflections in a 75 ohm coaxial cable. So I know that Z sub C is equal to 75 ohms. It has a relative dielectric constant of 4, epsilon r equals 4, terminated with a load impedance of 100 ohms. And we know that the frequency is 125 megahertz. We're going to assume that the stub is short-circuited and that it's made of the same material as the line itself. Those are the assumptions we will always make when we're designing a single stub tuner. Short-circuited and made of the same material as the line itself. So let's calculate the velocity. The velocity is C divided by the square root of epsilon r, which is 3 times 10 to the 8th divided by the square root of 4, which is 1.5 times 10 to the 8th meters per second. From that we can then calculate lambda. Lambda is the velocity divided by the frequency, 1.5 times 10 to the 8th divided by 125 times 10 to the 6th, that's megahertz, and that gives me 1.2 meters. So the wavelength of this line is 1.2 meters. I can then calculate the wave number. That's going to be 2 pi divided by lambda, which is going to be 2 pi divided by 1.2 meters, and that gives me 5.236 meters to the minus 1. I'm going to carry an extra digit of significance there just to make sure that I don't make any mistakes in that last digit. Let's calculate D2. So D2, and I don't want to rewrite the equation, but you know it's equation 25.56. This is the equation that we're about to use for D2. So let's come down here to D2. This is equal to 1 over 5.236 times the arctangent, or the inverse tangent, of the square root. Don't forget to do that square root when you're doing this calculation, because I sometimes do forget the square root, and that gives you the wrong answer. So don't forget that. 100 minus 75, the quantity squared. Take that square root and then do that inverse tangent, and you get 0.2463. You know what? I'll just carry it to 3 significant figures, as I always do in this class. I get 0.246 meters. This is the stub length. Always calculate the length first, and then you calculate the location. Then we can calculate D1, and again, I don't want to rewrite the equation, but it's equation 25.57. So that's the equation that we're about to use. So D1 is going to be equal to 1 over 5.236 times the inverse tangent of 100 minus 75 divided by 75 times the tangent. It's interesting that the tangent is inside the inverse tangent. 5.236 times 0.2463. Remember, this is K and this is D2. And when we do that calculation, we end up with 0.164 meters. and this is the distance from the load. So, single stub tuner. We don't have to have any sort of special esoteric coaxial cable with a special characteristic impedance. We don't lose any of the input signal because remember that this stub is going to have a purely imaginary impedance. So it doesn't actually absorb any energy. It redirects the energy, but ultimately all of the energy will be absorbed by the load. And so this has really the best of both worlds. It really does give us the opportunity to solve the problem in the best possible manner. So that's it. Today had a lot of equations in it, but the ideas were sort of, I think, direct building off of chapter 24. So we have our equation for the impedance at any point along the line, and then we have an equation for the input impedance of a line. We saw, and the length of the line is L. We saw that the input impedance, or just the impedance in general, is going to repeat itself every half wavelength. We're going to come back and see that again next chapter. And if the line is a quarter of a wavelength long, it has a special value of impedance, z sub c squared over z sub l. We actually used that twice in our discussion of impedance matching. If the line is short-circuited, it's going to be j z sub c tangent of kl. If it's open-circuited, it's negative j z sub c cotangent, which I sometimes like to write as negative j z sub c divided by the tangent of kl. Either of those would be fine. If you wanted to have a quarter wave transformer, it's very easy. You just have a piece of coaxial cable, or a piece of transmission line that is lambda over 4 in length, and whose impedance, whose characteristic impedance is the square root of z sub c times z sub l. Of course, the problem is that you often can't find that at the store. If you wanted to have a load impedance that would be have a parallel load put in parallel with it, then either you're going to use this equation and this method if the load impedance needs to be reduced, or you would use this equation and this impedance if the load impedance needs to be increased. And so you have your two choices there. You have to decide: am I trying to increase the load or decrease the load? And that will determine which method to use. Remember that if you're trying to increase the load, then you have to move that extra parallel impedance a quarter of a wavelength back from the load. And then finally, we have these two equations for the single stub tuner. This one represents the length, and this one represents the distance. Whoops, I shouldn't have drawn right through the equation. And this one represents the distance from the load.